Hello, another video being brought to you here by me, Mr. Sorrentino. This one dealing with section 1.5 of this course, which deals with linear equations, functions, zeros, and applications. Um, it's going to be the first chat or section of this textbook that goes into functions and zeros and applications. Just the equations as we move through the course is going to get a little bit more involved and, have different types of equations that you're able to handle as we move along. So this one is kind of a moderate level linear equation. You will see that some of the homework problems that are suggested from your textbook are much easier than this, and there might be some that are a little bit more involved in this. As we go through this lesson, and we get to some of the application problems, we might develop some other equations that, are a little bit different in structure than this, that we're going to solve as well. And as we go into dealing with the next section, 1.6, dealing with inequalities and finding their solutions, we get to situations where there's equations as well that we're going to solve there, that kind of fit some of the other molds that you're going to see here in 1.5. So between these two lessons, you're going to get a good sampling of equations along the way as well. And basically, when you're solving an equation, a linear equation, which is what we're starting off with. I mean, chapter 1 is basically with linear things. You had a few things that dealt with, graphing some other types of functions, but generally, a lot of what you were dealing with was linear. If I'm trying to solve an equation for a variable, my goal is simply to get the variable on one side of the equation isolated. That's it. So I want to basically have either, when all is said and done, x equals some number or some number equals x. Doesn't matter which one I get. So I, for one, like having x's on the left-hand side. I just get so used to this based on all the training I've had throughout my life. That's just the way I tend to always move it towards. So if you don't mind having the number equals x, by all means, So some of the choices that I'm going to show here are going to be made off of my preferences. Feel free to make sure that if you have different preferences, you adjust accordingly. So I'm going to want to get the x's on the left-hand side. So I'm going to subtract 7x from this side. The thing you have to remember is if I'm trying to move a number that's attached to the x through multiplication or division away from the x, I'm going to multiply or divide just that number. If I'm trying to move the entire term, I have to add or subtract it. And since 7x was positive, I'm going to subtract it from both sides. That would cause this to cancel. 4x minus 7x is a negative 3x. The minus 5 stays. The minus 2 stays. Now I'm going to add 5 to both sides because I want to start getting this x term alone. And since the negative 3x minus 5 was basically created through the order of operations, we were always going to assume that. I have to undo the order of operations to solve the equation to get x alone. So that's why one of the ways you want to kind of look at it, if you're using basic equation solving techniques, you're just simply undoing the order of operations, which means you're going to follow the order of operations in reverse. That premise works as long as there's only one variable in the equation. This had multiple x's, but they were all x's. If I start having x squareds and x's and other powers of x and other things like that, that's where it gets to be other methods have to be kind of integrated in there as well. So on this side, it's going to cancel. I'm going to have a negative 3x. On this side, I'm going to have negative 2 plus 5, which is 3. And then I'm going to divide both sides by negative 3. So on this side, I'm just going to have a single x, 1x technically, and 3 divided by negative 3 is negative 1. This is the solution to that equation. It's using a lot of the same manipulations that we had used earlier in this chapter when we were trying to get y isolated and things of that nature. Now, your calculator can be used to check this work. And again, I'm doing this on the Texas Instrument TI-83 Plus, TI-84 calculator. You're not required to necessarily have that. I strongly suggest you have one again. Um, and, I'm going to emphasize that. And those of you that get one, you're going to have a slight advantage. I'm not saying that, this is going to be something that's for people who can afford it, because, a TI-83 Plus calculator, you can get one on Amazon, $25, $30. I mean, so it's not going to break the bank. It's not going to be as sophisticated as what you see what I bring up here in this simulation version, but it's still going to be quite useful to you. But I could do the same. I could check this equation in a couple of ways. The first one is, and I'm going to go to a standard window on my graphing area, and I'm going to turn off the stat plot that I had before. Make sure you always have your stat plots turned off. Especially when you start going to more graphs. So I have my graphing window here. All I'm going to do is look at these two as being separate functions. Y equals 4x minus 5. And y equals 7x minus 2. And I'm going to graph those two things. So there's the 4x minus 5. And there is the 7x minus 2. And maybe let the y minimum go down a bit more. Let's say make that a negative 15. Just so we can see the intersection, better. Because that's what I'm looking for here. I'm looking for when these two expressions are exactly the same value. And that happens when they intersect each other. So right here is where I'm going to find that answer. So I want to find the x value where that would work. So what I'm going to do is I want to find this intersection. So I come up to second. I'm going to go to the calculate menu. And I'm going to go to 5 intersect. Now what this asks you to do is to pick the first curve, pick the second curve. Then I want you to do a guess, which you could do by either moving it as close to the intersection as possible. But since there's only one possible intersection between these two graphs, I really don't have to do that. And as you can see, x equals negative 1 is the solution for this. It makes both sides equal to negative 9, but it's the value of x being negative 1 that makes this happen. So there's one way we could check that answer. Another way we could, use the calculator to assist us in a situation like this. And that's what this method 2, I just showed you how to do that. Method 3 is kind of a combination of manipulating the equation so far and then putting that into a calculator. But the reason why we bring this one up is because it starts talking about a zero or root of a function, which is one of the things that we do want to talk about in this particular section. So, basically, one way I could also solve this equation graphically, if that's the way I want to go, is I'm going to write an equation set equal to 0. So I'm going to let one side of this equation be 0. I'm going to choose the right-hand side. So I'm going to subtract 7x from both sides. So I'm going to have that negative 3x minus 5 equals a negative 2. And I'm going to want that right-hand side to become a 0. So I'm going to add 2 to both sides. And I end up with negative 3x minus 3 equals 0. I'm looking for a value of x. It's going to make this expression equal 0. Well, how I would get that on my calculator at this point is that I would just now enter this expression in. So let me come here and let me clear these guys out. I was going to put in negative 3x minus 3. I'm going to graph that. And what I want to do is I want to see, so this line represents everywhere that y is a value given to me by negative 3x minus 3. I want to see where y is 0. So when I look at this, I want where y equals 0. Now I can see from this graph that it looks like it's at negative 1, but just to be on the safe side, I could also go to my calculator and choose choice 2. I want you to find the 0 of this function. Now it's going to ask for a left bound, which means I want to pick a value of x that makes this blinking cursor to the left of the intersection point. Since I think it's at negative 1, based on what I've done in the previous work I've done, I'm just going to put this at negative 2 so it's somewhere to the left. I can see a little boundary here. Depending on the calculator, you may not see the boundary as well. You'll definitely see the arrow up here. So, and then I'm going to let the right bound, which means I want to have an x value that puts this blinking cursor that's following this graph, on the right-hand side of this possible 0. So I'm going to let that just be 0. And so it's going to now find, where it crosses the x-axis between these two values. Now, the guess is like if I would happen to, have more than one place where this is passing through the x-axis between these two arrows, then I might want to put a guess. But since I usually do it so there's only one possibility, I really don't have to do anything for guess. And as you can see here, x equals negative 1 is again the solution. So there's different ways you can use the calculator as well to help you solve equations. So let's look at some examples now that where we could apply some equation solving. Because this is equation solving you should still basically remember from your algebra days. And see if we come up with solutions with these. So for example 2, we have John makes an investment of 4% simple interest. At the end of 1 year, the total value of his investment is $1,560. How much was originally invested? So what has to happen here is you have to know how to take percentages. And sometimes students forget this. The thing is, you're not just going to add 4 or 4% or 0.04, which we know that 0.04 is how we typically write 4% as a decimal. Some people just think you just add it, but it's 4%, it's always percent of something. And so basically, what should go on here is that at the end of 1 year, so I'm going to let y equal the dollar amount after X years. Okay? So what's going to go on with this is, well, I'm going to start with an initial investment. I don't know what that investment is. Okay, so I'm just going to call it for the time being, let's just call it A. So that's the amount I invest. That's what I'm looking for. At the end of 1 year, or after so many years, I'm going to have 4% added on to that. So I have to say, okay, well, I'm going to have 0.04 of that original amount added on. And so that's how I would do this particular formula, because now what's going on, we know that it's 1 year, so we know that X equals 1. So what the variable we're looking for here is a. So y is going to equal a plus 1, this becomes a 1, times 0.04a. These are like terms. They have the same variable, just different numbers in front. Technically there's a 1 here. And so here y is going to equal 1 plus 0.04 is 1.04, the original amount. Okay? This makes sense if you think about it, because if I invest an amount and I get 4% interest, at the end of that period of time, I should have 104% of what I originally had. So, so some of you can maybe take this shortcut and realize, well, if I have 4% added on, I'm going to have 104% of what I had before. So, now they're telling us that the total value of his investment, which means what it's all worth with the interest, is $1,560, which means that this is equal to my y value. So I know that 1056, or momentary mix up there, yikes, 1560 equals 1.04a. So that's the equation I needed to get to answer the question. Now, of course, I have to solve it. It's a pretty straightforward equation at this point, because all I have to do is divide both sides by 1.04. So a is going to equal 1560 divided by 1.04, and that's approximately equal to, well, not approximately, equal to $1,500 originally. So that's the answer to this one. On to example 3. The width of a rectangular room is 23 feet less than its length. The perimeter of the room is 134 feet. Maybe over a little bit. Find the dimensions of the room. So, although you probably don't necessarily need to do so, I am going to draw a little diagram of what's going on here. So we have this rectangular room, which has a length and a width. Now I'm going to call this L for length, and this is what we would normally call width, but the width, we're being told, is 23 feet less than its length, which means this is going to be L minus 23. The reason why, I don't want to interject too many variables is if I have multiple variables in an equation, it becomes hard to solve. I want to keep as few variables as possible, because now when I look at it, it says the perimeter is 134 feet. Well, the perimeter, which I'm just going to say is P, would be length plus width plus length plus width. And if I had this, or even if I simplified it and said it's 2L plus 2W, I wouldn't be able to solve that very easily, because the fact of the matter, with two variables still in play, there's combinations of answers that would possibly work. So now with this piece of information, I can now say, well, I can now put this in terms of one variable, which is going to basically mean I'm going to get only probably one answer. And then for linear equations, at least, that's what tends to happen. So I can now change this to 134 equals 2L. And since W is equal to L minus 23, I can replace W with L minus 23. So I would have 134 equal to 2L plus 2L minus 46. And so 134 equals 4L minus 46. So now I'm into an equation now that can be solved. I got it simplified as much as I can. Now I'm ready to isolate the variable, which in this case is L. So I'm going to add 46 to both sides. And when I do that, I'm going to get 180 equals 4L. Dividing both sides by 4, I get that L equals 45. Which means that this is 45 feet. Now, I have to go back and make sure I answer the question I'm being asked. Sometimes students will stop short and say, well, I got a letter equaling a number, I'm done. Yay. But the thing is, that 45 is part of the answer because it's asking me to find the dimensions. So that means I want to find the length and the width. I now know this width is 45 minus 23, which is 22 feet. So the dimensions of the room are 45 feet by 22 feet. And that answers the question. So always make sure to go back and make sure the question that was asked is the one that's being answered. Don't say, okay, find the dimensions of the room, and you say 45 feet. Well, that's one dimension. What's the other one? So make sure you know what the dimensions are, make sure you know what's being asked, and answer the question being asked. Last example deals with distance, rate, and time a little bit. And some students always get stuck on these a little bit, but let's kind of map out the situation here. Angela's kayak travels 14 kilometers per hour in still water. That means that's how fast he could paddle. If the river's current flows at a rate of 2 kilometers per hour, how long will it take him to travel 20 kilometers downstream? So, again, we have this formula, distance equals rate times time. It's a very simple setup, but we have to make sure we put things in the right place and that we're accounting for everything. For instance, what it's asking for is how long will it take. That means that t, time, is the variable here. That's what we're going to eventually be looking for. That means that r and d should be known based on the information they gave us. And, also applying any knowledge that we may have. 20 kilometers is the amount of distance that Angela needs to travel. So we know that this is 20. The rate is a little trickier because they give you a rate in kilometers per hour for still water, but they also say that the river's current flows at 2 kilometers per hour. If you're going downstream, that means the current is working with you. So Angelo, his rate should be what he can produce himself along with the 2 extra kilometers per hour that the current should be pushing him. So his actual rate here is 16 kilometers per hour. And so it's going to be 16, of course, times t. Again, a very simple equation at this point. I just have to get t alone, and I'm going to divide both sides by 16. That means that t equals 20 over 16, which equals 5 over 4, which is 1.25 hours. And I know it's hours because we had kilometers per hour. 1.25 hours, I could also say it's 1 hour, 15 minutes. because 15 minutes is a quarter of an hour, because an hour is 60 minutes. So, I can answer anyway. It's not asking me a specific, way of answering it, but those are all going to be possible ways that the answer could be represented in a multiple choice if you would be given that. Oh, that's all I have for this particular video. If you have any additional questions with this, please make sure to reach out. Some more equation circumstances will show up in 1.6 as well. So if you feel that there's more equations you would like to see, have a look at the 1.6 video as well. Although it's dealing with inequalities, there's going to be a lot of equation solving in it. So you could have a look at that as well to help answer some of these questions you might have as well. But until the time I see you in class, have a good day, everyone, and I'll see you around.